So, we will now see some of the example of EBSD. EBSD, as I have discussed and shown you in the lab, is extensively used now for different microstructural analysis. So, I am going to show you one example which we have carried out to analyze the solidified microstructure, in which EBSD was used to show how the gain refinement happens during undercooling experiments. Well, as you know that gain refinement of any material can be either intrinsic or extrinsic. In case of extrinsic gain refinement, we add certain refinement agents like titanium boride in case of aluminum alloys, but in case of intrinsic gain refinement, we do not add any elements or any gain refiner. Gain refinement happens because of the fragmentation of the dendrites which form during solidification of the alloys or metals, and this can happen because of many reasons. So, one of the reason is the recrystallization and the recovery and recrystallization which takes place during the solidification or just after the solidification event. As we know, the solidification leads to volume change of the material from the liquid to solid, and this can lead to stress generation, and stress can cause at high temperature recrystallization, and recrystallization can lead to gain refinement. So, let us see one example like that. So, the one which we have done in our research is from iron germanium phase diagram. So, if you look at iron germanium phase diagram, it is basically crowded with so many phases, but I am going to consider only the alloy which 18% germanium, the one which I marked by red. And as you see here, if we start solidifying from the liquid state, it will form alpha Fe, that is BCC alpha iron with certain amount of germanium, and then just below the solidus temperature it will undergo ordering. So, therefore, BCC alpha iron will become B2, and then further cooling leads to DO3, or that is second order ordering. So, therefore, this ordering in the solid state can also lead to stress generation, and that can also cause recrystallization to happen. So, by knowing that, we are going to see how this EBSD technique can be used to analyze the microstructures. I will show you some microstructures which are basically obtained by conventional optical microscope, and then I will show you some analysis by EBSD. So, as you see, if we undercool the alloy by only 50 degrees, that is very small amount, we could see the microstructure consisting of grains like this, and with each grain we can see segregation patterns. That is basically signature of the solidification at low undercooling. And not only that, we can see even the dendrites present within the grains, and I am marking some of the grains here. As you can clearly see here, this is another grain, and within the grains you can see the dendritic structure built in. So, therefore, at low undercooling, the solidification happens normally by dendritic manner, and as you increase the undercooling level by more than 100 degree, 110, you can see the grain structure much little bit finer than the earlier one, and we can also see the segregation pattern inside the grains, inside each grain with the dendritic morphology remaining in the grain. Now, once we do the EBSD analysis, we can find out the nature of these gain boundaries, okay, which are there and in this microstructure. And if we look at it, most of the gain boundaries here are shown as a function of misorientation angle, okay, number of grains as a function of misorientation angles. Misorientation basically means one grain with respect to the other grain is misoriented by a certain angle, and that is basically the reason for the gain boundary. We know that within one grain the orientation of the crystal is same. As we cross over the boundary, we go to the next grain, orientation changes, and this orientation change is represented by misorientation angle in the EBSD. So, this data is directly obtained from EBSD after just collecting the EBSD informations and plotted as a number fraction of grains versus misorientation angle. As you see, most of the grains are actually having misorientation angle more than 25 degrees, very small amount is basically having less than 5 degrees. So, most of the gain boundaries are here high angle gain boundaries, that is very clear. So, therefore, one can obtain the nature of the gain boundaries from the EBSD analysis directly. Now, this is the one which I am showing if you undercool by 130 degrees K, 30 K, and you can see in the microstructure there are big grains like this, and within the big grain there are small grains. This are the small grain presence. So, by looking at this optical micrograph, any what's called avid reader of this what's called microstructure or understand whoever having good understanding the microstructure will tell that these grains are actually formed by some means from the big grains. So, therefore, the boundaries of these grains will be small angle grain boundaries, and these big grain boundaries will be large high angle grain boundaries. This is what is we find in when case of doing EBSD. If we do EBSD and then find out the misorientation angle plot versus fraction of grains as a function of misorientation angle, we can see that there are large number of grains having misorientation angle less than 15 degrees. In fact, if you look at it less than 10 degrees, there are large number of grains present. So, these grains actually are small angle boundary, they have the small angle grain boundaries. On the other hand, there are grains which are having large angle grain boundaries which are present here, like the one which I shown you, and there is another one I can show you here. So, that means there is a distinct change of the grain boundary, nature of the grain boundaries as the undercooling increases. As we know, undercooling increases means driving force for solidification increases, so there will be no stress more stress generation, and chances of recrystallization is more. So, it looks like that these grains which are formed here may be due to recrystallization, which will be clear more as I go on. If we undercool it even little deeply about 140 K, I am just showing you the optical micrograph, you can see the big grains here again, and within the big grain there are so many small grains present, similar nature which I have shown you just one slide before. And if you zoom out the picture, you can see the segregation of dendritic pattern inside the grains actually. If you undercool it even much higher level by 190 K, which is very extensively high undercooling, you can see the big grains here present, and within the big grains there are so many small grains present. And EBSD analysis done on this sample, it can be represented as the number of fraction of grains versus misorientation angle. Here again you see the large number of grains having less than misorientation angle less than 10 degrees, signifying that they are small angle grain boundaries. There are large number of small angle grain boundaries which can be seen here also. On the other hand, there are also large number of grains which high misorientation angle, so they are these big grains which are actually this. So, this two things are very clear from this analysis. One is that there is a subsequent grain refinement, grains are getting smaller and smaller as your undercooling increases, and at the same time these finer grains are basically having small angle boundaries. So, therefore, just by doing this EBSD analysis one can tell that these grains most likely has formed by recrystallization, and if they have formed by recrystallization, obviously there will be a distinct texture of the material also will be visible. So, if I just do a what's called grain map and plot it in different color format, we can see there are very large grains. You can see this one is a very large grain with pink color, and within this large grain there are so many small grains present, and there are small grain present here and there also. And if we get this what's called inverse pole figure, you can see these pink grains are very close to 001 orientation, the green actually 101 orientation, and the blue or rather little bit bluish grains which are present very small, the small ones are actually 111 orientations very clearly. So, you can see the depth of information which one can obtain from one sample by analyzing the EBSD. And if we do this again from the same grain, if I plot the grain boundary, number of fraction of grain boundary versus misorientation angle, again we see large number of grains as a base, small misorientation less than about 7.5 degrees, and they are actually having small angle grain boundaries, whereas there are grains which are having large angle grain boundaries. So, grain boundary information very easily obtained. Now, as far as this texture is concerned, which I just now I mentioned, if I just use this and put a plot inverse pole figure from the grain map, you can see there is a fibrous texture present. You can see this kind of nature of this texture clearly present on 111 orientations in a typical RD and TD plot, and there are obviously orientations of the grains which are predominantly present in along these directions. So, one can actually obtain exactly the nature of texture from this analysis. And if we do careful analysis, that means if we take inverse pole figure of along 001, 110 and 111 of this grains or this large number of grains, we can actually get an idea of the kind of texture presence. You can clearly see that along 110 directions the picture is much more clear, showing the distribution of the orientation of the different grains and signifying that there is a distinct texture. So, this itself tells us that the grains has formed by recrystallization and there is a texture of the grains present in the sample. So, by this way we can actually understand the whole mechanism of grain refinement in an alloy where there is no grain refinement present, but because of undercooling grain refinement happens. And this was not possible without EBSD. Obviously, one cannot do with any other analysis than EBSD, because in TEM you cannot see so many grains. As you have seen, the grains are very big, so it is not possible to do analysis by transmission electron microscope. Only possible way to do analysis is EBSD. Well, so now I am going to basically show you different pictures, different analysis which you have done while giving you the demo in front of the SEM in the Department of Material Science Engineering at IIT Kanpur. And here we are looking at another sample of stainless steel, austenitic stainless steel 316, and as you know, it is basically it has FCC crystal structure containing about 18% chromium and 8% nickel, and one can take the sample and then analyze it again, the grains, grain boundaries, misorientations and many other features. This sample was basically prepared by simple casting route and followed by rolling, and so therefore we expect some certain kind of what is called recrystallization happen in during the processing. What you see here is basically a grain map, okay, of the stainless steel sample, and after taking the EBSD data, and here I am showing you grain boundaries by plotting different colors. Okay. So, if you look at, if the grain boundary is having white and then it is a high angle grain boundary, the misorientation will be 15 to 62.8 degrees, that is basically definition. And if the grain boundary is shown by blue color, which are there are so many large number of grain boundaries are present, having grain misorientation angles between the grains to be 7.5 to 15 degrees, and if it is in the green color, it is even less than 7.5 degrees. So, as you can see, there are a large number of grains having less than 7.5% orientation, 7.5 degree orientation differences. So, that clearly tells us there is certain kind of what is called texture. First of all, there is certain kind of grain refinement happened because of the recrystallization or whatever happened in the rolling process. Now, one can actually do this grain map from the EBSD data, and that is what shown here. You can see even the very clearly the grain map. One can even see the twins in the stainless stacking faults in stainless steel. This is the one, there is another one, there is another one, there is another one, lot of. And from the grain map, which is very clear grain map, one can actually see this pole where 001, 111 and 110 FCC is plotted. Here you can see that this red color grains are again having orientation close to 001, and they are there but not very large. On the large number of grains actually green color, which have orientation is 101 type. So, therefore, predominantly grains are having 101 orientations in this crystal, and presence of the grains of what's called 111 orientation is very less, and even the grains of 001 orientation is little higher than the 111 orientation, but still it is predominantly 101 type of orientation present in the grains. Now, one can actually take the inverse pole figure and analyze the basically pole figure, analyze this different texture. This is along 100, 110, 111. As you can see here, along 110 is not clearly visible what kind of texture is present, but along 110 it is very clear that along 110 there are distinct regions where the two orientations are very fixed. So, there is a certain amount of texture presence. Along 111 also you can see clearly this was called predominantly featuring orientation present in the sample. In fact, one can do better nowadays with the help of these better softwares. So, what you can see here that the number of grains having different orientation is plotted here. This is 001, this is 101, this is 111, and you can see that predominantly the green, large number of green areas present here. So, therefore, grains are predominantly 101, which I just now I showed you.